Welcome! In this session, we'll tackle an interesting problem from LeetCode, problem number 1903, titled Largest Odd Number in String. We'll explore the challenge, break it down step by step, and discuss efficient approaches to solve it. Let's dive in. In this problem, you are given a string number, which represents a large integer. Your task is to find the largest valued odd integer that can be formed as a non-empty substring of number. If no odd integer exists, you should return an empty string. Remember, a substring is simply a contiguous portion of the string, and an integer is considered odd if it is not divisible by 2. The input consists of a string of digits, and the output should also be a string representing the largest odd-valued substring, or an empty string if there are no odd numbers. For example, if the input is number equals 52, you need to determine the largest odd-valued substring within it. The output for the input number equals 52 is 5. The substrings of the string 52 are 5, 2, and 52. Among these, the only odd integer is 5, and since there are no larger odd values, 5 is the result. Now consider the input number equals 4206. In this case, the output is an empty string because all possible substrings of 4206 evaluate to even integers, meaning there are no odd numbers to select. This demonstrates that if no odd digit exists in the string, the output will simply be an empty string. For the input number equals 35427, the output is 35,427. Here, the entire string is an odd integer, and because it is the largest possible odd-valued substring, it is returned as the result. Moving on to the constraints, the length of number can go up to 100,000 characters, making it important to consider efficiency in your solution. The string number will only contain digits from 0 to 9 and will not have any leading zeros. Additionally, there are edge cases to keep in mind, such as when the string contains no odd digits, as is the case in number equals 24680, where the output is an empty string. Other edge cases include situations where number is a single-digit odd number, such as number equals 3. Here, the output is simply the string itself because it is already the largest odd-valued substring. If the largest odd-valued substring happens to be the entire string, such as in number equals 13579, the output is the entire string. Another scenario involves strings with trailing odd digits, like number equals 123456. In this case, the output is the substring from the start of the string up to the last odd digit, which is 12,345. These examples illustrate the variety of cases you should account for when designing your solution. To solve the problem, we first considered a brute force approach. The intuition here is straightforward. If we generate all possible non-empty substrings of the input string, we can check each substring to see if it represents an odd number. Specifically, we look at the last digit of each substring to determine if it's odd, since only the last digit affects a number's oddness. The largest odd substring can then be tracked as we iterate through all possibilities. However, this method is computationally expensive. Generating all substrings has a time complexity of O(n) squared, and checking each substring adds another layer of O(n), resulting in an overall complexity of O(n) cubed. This is impractical for large strings, as the cubic time complexity leads to significant inefficiency. To address these shortcomings, we explored an optimized approach that leverages key observations about the problem's structure. The optimized approach works by iterating through the string from right to left. The key idea is that the largest odd-numbered substring always ends at the rightmost odd digit. This is because removing digits from the end of a number only decreases its value. As we traverse the string, we check if the current digit is odd. When we find the first odd digit, we return the substring that starts from the beginning of the string and ends at this digit. If no odd digit is found after iterating through the entire string, we return an empty string. This approach is highly efficient because it avoids generating unnecessary substrings and directly focuses on identifying the largest odd number. With a time complexity of O(n), as we only traverse the string once, this method is optimal for large inputs. While other solutions exist, such as using binary search after pre-computing odd digit positions, these add unnecessary complexity compared to this direct and efficient strategy. The breakthrough insight for this problem was recognizing that a number's oddness is determined solely by its last digit. This observation allowed us to simplify the problem significantly and design a solution with O(n) time complexity. Although the brute force approach is conceptually simple, its computational expense makes it impractical for large inputs. Similarly, while the binary search alternative is clever, it introduces additional overhead that isn't necessary given the simplicity of the optimized solution. The chosen strategy minimizes both time complexity and implementation effort, making it the most practical choice. The final implementation is elegant. We iterate through the string from right to left, checking each digit until we find an odd one, and then return the corresponding substring. This approach also has a space complexity of 1, as no additional data structures are required. Here is the Python implementation, which directly embodies this strategy. We iterate through the string, check oddness using a modulo operation, and return the largest odd substring if found, or an empty string otherwise. The problem asks us to find the largest odd-numbered substring from a given string number that represents a non-negative integer. If no such substring exists, we return an empty string. One possible approach to solve this is through brute force, by generating all possible non-empty substrings of number, determining if each substring represents an odd integer, and keeping track of the largest one. To achieve this, we start by initializing a variable max_odd to store the largest odd-numbered substring found so far. This variable is initially set to an empty string. Then, we loop through all possible starting indices of the string, and for each starting index, loop through all possible ending indices. For every combination of start and end indices, we extract the substring and proceed to evaluate it. While this approach is straightforward and guarantees correctness, it is computationally expensive due to the large number of substrings generated, especially for longer input strings. Once we generate a substring S, the next step is to check whether it represents an odd number. A number is odd if its last digit is 1, 3, 5, 7, or 9. Instead of converting the entire substring to an integer, we can simply check the last character of S to determine its oddness. If the substring is odd and its integer value is greater than the current value of max_odd, we update max_odd to this substring. After checking all possible substrings, we return the value of max_odd. If no odd-numbered substring is found during this process, we return an empty string. While this approach works for smaller inputs, generating all substrings and checking each of them for oddness is not efficient, especially for strings with large lengths. This limitation prompts us to explore more optimized methods. To improve our solution, we can make a few observations. First, checking oddness can be optimized by avoiding unnecessary conversions. Instead of converting a substring to an integer, we can directly examine its last character to determine if it is odd. This small optimization reduces computational overhead. Next, we analyze the complexity of the brute force approach. Generating all substrings involves n squared substrings for a string of length n, and each oddness check takes 1, resulting in an overall time complexity of n squared. However, this quadratic complexity renders the brute force solution inefficient for larger strings. Thus, while the brute force method is simple to implement, its limitations in scalability highlight the need for a more efficient approach. To solve the problem more efficiently, we can use an optimized approach that involves scanning the string from right to left. The intuition here is that the largest odd-numbered substring must start at the beginning of the string and end at the position of the last odd digit. By scanning the string in reverse, we can identify the rightmost odd digit and immediately determine the desired substring. The steps are straightforward: traverse the string in reverse order, and for each character, check if it is an odd digit. If an odd digit is found at index I, the substring number, I+1, represents the largest odd-numbered substring. If no odd digit is found during the scan, we return an empty string. This approach eliminates the need to generate all substrings and reduces the time complexity to n, making it significantly more efficient. Scanning the string from right to left is effective because it ensures that the first odd digit encountered corresponds to the largest odd-numbered substring. The time complexity of this method is n, as we only traverse the string once. Additionally, it is space efficient, requiring only 1 extra space since we do not store or generate substrings explicitly. The input string number is directly used for substring operations, and a single variable is sufficient to store the result. This combination of efficiency in both time and space makes the right-to-left scanning approach ideal for solving this problem, especially when dealing with large input sizes. Let's walk through an example to illustrate the two approaches. Consider the input number equals 4206. Using the brute force method, we generate all possible substrings: 4, 42, 420, 4206, 2, 20, 206, 0, 06, 6. None of these substrings end in an odd digit, so we return an empty string. For the optimized approach, we scan the string from right to left, checking each character: 6, 0, 2, 4. None of these digits are odd, so we again return an empty string. Now, for the input number equals 35427, the optimized approach scans from right to left, encountering the digit 7, which is odd. The substring number, 5, equals 35427 is the largest odd-numbered substring, so we return it. This demonstrates how the optimized approach quickly identifies the result without generating unnecessary substrings. When solving this problem, it's important to account for edge cases. For an empty string, the result is straightforward: return an empty string. If all digits in the input are even, we also return an empty string, as no odd-numbered substring exists. For an input with a single odd digit, such as 7, the digit itself is the answer. Lastly, for large inputs, the optimized approach ensures that the algorithm runs efficiently, even for strings with lengths up to 10 to the power of 5. These edge cases highlight the robustness of the right-to-left scanning method and its ability to handle a variety of scenarios effectively. This Python solution for LeetCode problem number 1903, largest odd number in string, is efficient and straightforward. The goal is to find the largest substring of the given string number that represents an odd integer. If no such substring exists, we return an empty string. The solution begins by iterating through the string number from right to left. This approach works because the largest substring ending with an odd digit will define the result, as the string must be contiguous and odd numbers are determined by their last digit. Using a reverse traversal ensures we find the largest valid odd-numbered substring without unnecessary checks. For each character during the traversal, we check if it represents an odd digit. This is achieved by converting the character to an integer and checking if the remainder when divided by 2 is non-zero. Int number %2 equals 0. If an odd digit is found, the function immediately returns the substring from the start of number up to and including the current index, number, i+1. If the loop completes without finding any odd digit, the function returns an empty string. This handles cases where all digits in number are even. The time complexity of this solution is O(n), where n is the length of the input string number, as we traverse the string once. The space complexity is O(1), as no additional data structures are used. This makes the solution efficient and well-suited for large input sizes. This is the Java implementation of LeetCode problem number 1903, largest odd number in string. The logic mirrors the Python solution, iterating through the string from right to left and checking if each character represents an odd digit. If an odd digit is found, the substring up to that index is returned. Key differences in Java include the use of type declarations, the char@, method for character access, and the substring method for extracting the desired portion of the string. This problem asks us to find the largest substring of a given string that represents an odd number. To solve it, we need to understand that an odd number always ends with an odd digit, namely 1, 3, 5, 7, or 9. With this insight, the task becomes finding the rightmost odd digit in the string and returning the portion of the string up to and including that digit. For example, if the input string is 52 foot, we start by examining the digits from right to left. At the first position, we encounter 2, which is even, so we continue. At the next position, we find 5, which is odd. Since this is the rightmost odd digit, we return the substring up to this position, which is 5. Thus, the output in this case is 5. Now, let's look at a more detailed example with the input string 4206. Here, we again start iterating over the string from the rightmost digit. First, we check 6, but since it is even, we proceed to the next digit. Then we check 0, which is also even, so we move on. Next, we check 2, which is even as well, so we continue. Finally, we check 4, which is still even. At this point, we've examined all the digits and found no odd numbers. Since there are no odd digits in the string, there is no valid substring that can represent an odd number, and the output is an empty string. For the next example, consider the input string 35,427. Starting from the last digit, we first check 7. Since 7 is odd, we know that any substring ending at this position will form an odd number. Therefore, we can directly return the entire string up to and including this position, which is 35,427. The key here is that as soon as we encounter an odd digit during our iteration, we can immediately stop and return the appropriate substring. Thus, the output for this example is 35,427. This algorithm works efficiently because it leverages the insight that the largest odd number must end with the rightmost odd digit. By iterating over the string from right to left, we ensure that we find this digit in a single pass. The time complexity of the solution is O(n), where n is the length of the string, as we only loop through the string once. It also handles edge cases effectively, such as when there are no odd digits, which correctly returns an empty string, or when the entire string is odd, which returns the full string. Even single character strings, like 5, are naturally handled by the loop. Overall, this solution is both straightforward and optimal, making it a great way to solve the problem. The time complexity of the solution can be analyzed by breaking down the operations. First, the algorithm iterates through the string number in reverse order, starting from the last character and moving toward the first. In the worst-case scenario, this loop will iterate through all the characters of the string, so for a string of length n, there will be exactly n iterations. Within each iteration, the operations include converting the current character to an integer, which takes constant time, O(1), and checking whether the integer is odd using the modulo operator, which is also O(1). If an odd number is found, the algorithm slices the string up to the current index to return the result. In Python, string slicing is an OK operation, where k is the number of characters in the slice, and in the worst case, this could involve the entire string, making it O(n). However, since the slicing operation is performed only once, it does not significantly affect the overall complexity. As a result, the dominant factor is the loop, which gives the overall time complexity of O(n), where n is the length of the input string. To summarize the time complexity, in the best case, the algorithm finds an odd digit at the very last character of the string, requiring only O(1) operations. In the worst case, the algorithm has to traverse the entire string to find an odd digit, requiring O(n) operations. For the average case, the complexity depends on the distribution of odd digits within the string, but for large strings, it generally aligns with O(n). Now, considering space complexity, the solution uses a constant amount of extra space for variables, such as the loop index and temporary computations like converting a character to an integer. String slicing in Python does not inherently allocate additional memory, as it creates a view into the string. However, if the slice string is stored or returned to the caller, the memory usage depends on the size of the slice. In the worst case, storing the result string can require O(n) space. Therefore, the space complexity is O(1) if we exclude the result string and O(n) if we include it. Comparing this optimized solution to a brute force approach highlights its efficiency. A naive solution might involve generating all possible substrings of number, checking whether each substring ends with an odd digit, and then keeping track of the largest valid substring. Generating all substrings would require O(n)² operations, as each substring involves a new starting and ending index. Checking each substring for oddness would similarly take O(n)² in the worst-case scenario, and comparing substrings to find the largest would add another layer of O(n)² complexity. This results in an overall time complexity of O(n)² for the brute force method. Additionally, the naive approach would require storing all substrings, leading to a space complexity of O(n)² in the worst case. In contrast, the optimized solution only requires a single traversal of the string in minimal space, making it far more efficient. In summary, the optimized solution achieves a time complexity of O(n) and a space complexity of O(1) or O(n), depending on whether the result string's memory is included. On the other hand, the naive approach has a time complexity of O(n)² and a space complexity of O(n)². Clearly, the optimized solution is significantly more efficient for larger input sizes, both in terms of time and space. This makes it the ideal choice for solving the problem, particularly when dealing with long strings. When solving this problem, there are a few common mistakes to watch out for. First, developers sometimes misinterpret the problem statement, particularly around the concept of substrings. Remember that substrings must be contiguous sections of the original string, and their order cannot be changed. Non-contiguous subsequences are not valid. Another issue is ignoring leading zeros. Substrings like 007 may look valid at first glance, but they evaluate to the number 7, not 007, which can lead to incorrect comparisons. A third pitfall is relying on a brute force implementation. Generating all possible substrings and checking each one for oddness results in an n³ time complexity, which is unscalable for larger strings. Finally, edge cases are often overlooked. For instance, strings with no odd digits like 2468, single-digit strings, or strings with repeated characters such as 111111 require special attention to avoid runtime errors or incorrect results. Another mistake to be cautious about is forgetting to convert substrings to integers during comparisons. If you compare them as strings, the comparison will be lexicographical, not numerical, which can lead to logical errors. Now, when preparing for interviews, focus on developing an optimized solution rather than brute force. A key pattern in string problems is to avoid explicitly generating substrings, as that approach is inefficient. For this problem, a great optimization is to iterate from the end of the string to the beginning. The first odd digit you encounter determines the largest odd-numbered substring. The key insight here is that a number is odd if its last digit is odd. This simple property drastically simplifies the task since you only need to check suffixes. During interviews, it's a good idea to start by explaining the brute force approach to show problem comprehension, then transition to optimizations. Always test your solution against edge cases, such as strings with all even digits, single-digit inputs, or very large strings. This problem also relates to several others on LeetCode, which can strengthen your understanding of similar patterns. For example, LeetCode 485, max consecutive ones, involves identifying contiguous subsequences that satisfy specific conditions. LeetCode 567, permutation in string, requires substring checks and often employs sliding window optimizations, which is another useful technique. LeetCode 3, longest substring without repeating characters, focuses on efficient substring analysis and traversal. And LeetCode 1758, minimum changes to make alternating binary string, deals with string transformation and condition checking. Practicing these problems can help you recognize recurring patterns in string manipulation and optimization techniques, which are invaluable for tackling this and other related challenges. To solve this problem, there are a few approaches to consider, each with its own trade-offs. The most optimized approach involves a linear scan from right to left. The idea is to find the first odd digit and use it to determine the largest odd-numbered substring. This method is highly efficient with n time complexity, but it doesn't explicitly generate substrings, which might feel less intuitive for beginners. Another approach is using a sliding window technique, which dynamically checks suffixes as potential candidates by adjusting the window size based on the position of the last odd digit. While also this method can be more complex than necessary for this specific problem. Finally, there's the brute force approach. By generating all substrings, checking each one for oddness, and tracking the largest, you can solve the problem in a straightforward way, but at the cost of n³ time complexity, making it impractical for large inputs. Each method has its merits, but for efficiency and simplicity, the linear scan is the best choice for this problem. Great job! To wrap up, we reviewed the key points of the problem, including the optimal solution and its efficiency. Remember, mastering these techniques will help you tackle similar problems in interviews and real-world scenarios. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!